will be Prof. Srinivasan, Raj, on the system engineering technologies for water energy optimization, looking at opportunities for small and medium-sized enterprises. Over to you, Raj.
Okay. Thank you, Togo. Thank you for the great introduction. Good morning to everybody.
Morning.
Can you confirm that you're able to see my slides?
Yes, on my side, I can see the slide.
Perfect. So thank you, Toko, for the confirmation.
Oh, yes, yeah, I can see it now. Yes.
So once again, a warm welcome to all the participants in today's webinar. Like Professor Mazozi just mentioned, we have had a long period of collaboration between Professor Mazozi's group and my group here in earlier in Singapore and now here in India. This seminar, this workshop is an outcome of a project that we have been working on together for the last 3 years. And what we intend to showcase both in the presentations today and tomorrow is how the traditional challenges related to water, energy, that the chemical industry or the process industry in general faces has some solutions. These solutions have traditionally been adopted by large companies. They have both the access to the technology as well as the required expertise in-house to be able to develop, deploy, and continuously run their operations incorporating these technologies. What I would like to do in this first presentation is to share with you some thoughts on how these technologies can equally well be made available and adopted by the smaller companies. In India, we call them as micro, small, and medium-sized enterprises, MSMEs. Traditionally, these are companies, as I will elaborate on later, which have fairly small capex. Their facilities are not super sophisticated. They have manpower primarily to do the manual work. Probably they would not have an in-house R&D department, leave alone people with knowledge of expertise of modeling and optimization and so on. So it would at first sight appear as if systems engineering technologies that many of you in the audience today would be familiar with, it would appear that these systems engineering technologies are not ready for SMEs. What I would like to do today is convey to you that, in fact, with some additional effort on the part of researchers, both academic and industrial researchers, it is possible to take these same technologies and make them kind of edible, make them of use to MSMEs. We do have a panel session at the end of, towards the end of this session. So we will take questions and clarifications from the audience during the panel. But in the meantime, if you have any comments you would like to make, feel free to put them in the chat box, and the speakers would answer them as time permits. So with that brief prelude, let me kind of set the stage for what I would like to cover over the next 25 minutes or so. I think everybody in this room is aware that over the last 6-7 years, there's been a concerted global effort to one, formulate, and to tackle the overall sustainability challenge that this planet that we call home is facing. The United Nations led the development and formulation of what are now called as the Sustainable Development Goals. There are 17 of them. Many of them are further subdivided. But broadly, we know that there has been a call to action for every country, for every company, for every industrial sector, for every city, and so on, to look at how they impact their population, their customers, in terms of ensuring food, health, education, gender equity, and so on each of these 17 different dimensions. Now, the chemical industry has also been called to answer to this goal. The reason for that is very simple. The chemical industry is, in fact, a large consumer of both energy and water. My plot on the top left gives you an example from the US industrial sectors. And you can see that the bulk chemical industry and oil and gas together account for nearly 40% of total energy consumption. There are a number of other industries which also contribute significantly, but clearly the chemical industry has a large footprint in terms of energy. Now, the chemical industry has been sort of aware of its impact on the energy pie, and it has, at least for the last 30 years or so, looked at how it can reduce its specific energy consumption. So the plot on the bottom shows you the relative improvement in the specific energy consumption. This is from the chemical industry in the European countries, the 27 European countries. And you can see that compared to a benchmark of 100 units of energy consumption, specific energy consumption in the year 1990, we have seen a reduction of nearly half in the last 20 years. So our energy consumption per unit production has come down by 50%. Clearly, this is an excellent achievement, but much still needs to be done. Now, if you look at the picture on the right, this is a pictograph put out by the World Business Council for Sustainable Development in response to the UN 17 SDG goals. And what they highlight, what this pictograph highlights, is that if you look at the opportunities for the chemical industry, it has avenues to tackle food, water, health, energy, and infrastructure in various different ways. Now, this could be in the form of increasing water stewardship, improving energy efficiency, and so on. And these obviously are all multi-tiered, multi-dimensional opportunities. And this is what I really want to address in today's presentation. So how can the chemical industry go about making an impact on food, water, health, energy, and infrastructure? If you look at it from the point of view of a chemical engineer, this can happen in the form of 3 Ps. The 3 Ps stand for by looking at the products the chemical industry produces, by looking at the processes that we use to make these products, and then looking not just within the boundary of the chemical manufacturing facility, but also looking at partnerships with various entities. So these can lead to actual concrete action in the form of low carbon economy, in terms of circular economy, and in the last 5 years, this focus on digitization, using information as a means to make a dent on all of these things that we care about. In today's talk, I'm going to be primarily focusing on water and energy. So what the World Business Council for Sustainable Development highlighted was that there is a clear opportunity to make a dent on water consumption, use, and then the wastewater which is produced by increasing the water use efficiency across all sectors of the chemical industry, by reducing how much fresh water we can we tap for running our processes, and then using integrated water resource management and developing adequate capabilities, including infrastructure, to do that. Similarly, if you look at energy efficiency, there are very clear opportunities to improve energy efficiency and reducing the amount of both fossil fuels, but also any kind of energy source that we require in order to make our products. So historically, if you look at the last 45, 50 years, a branch of chemical engineering, what I would call as systems engineering or process systems engineering, has been tackling these kinds of issues. In a sense, it's bread and butter for systems engineering to look at the process and its efficiency. And this has been done using a variety of tools, techniques, and so on. I will not dwell into the details of these, but I will grossly generalize by saying that the tools and techniques of systems engineering primarily originate from models. We build a model of the plant or the process. We use this model to figure out how best to design the process, also how best to operate the process. And in order to do both this optimal design and optimal operation, we do various levels of analysis. Oftentimes, or almost invariably, it's not possible to do a variety of experiments on the real plant or the real process. So we do this analysis almost invariably on models of the process. These models could be built using first principles, using our knowledge of mass balance, energy balance, and various other physics-derived insights. And more recently, we build on AI, artificial intelligence, machine learning, advanced model-based control, etc. Process integration, process intensification, all of this to figure out how to improve the efficiency of the resources, how to take into account the availability of the resources, how to incorporate that with the demand for the products, and leading to improved products, improved processes, which then generate less waste. So I would say that over the last 40 some years, PSE, Process Systems Engineering, has been tremendously successful in deriving insights, which have then been adopted by industry. Now, if you look at where we are going with this, we have done this with traditionally with large-scale plants, which are well instrumented, where lots of data is available. We have done this where the amount of expertise required has been traditionally very large. So you would see large multinational companies like the Dows, DuPonts of the world, the Exxon Mobils, the Shells, the British Petroleums of the world use these techniques almost daily. They would have large in-house teams, 20 to 50 people in their R&D organizations doing these kinds of analysis day in and day out, ensuring efficiencies go up. As I alluded to in my opening notes, what has been not as much of focus, especially of the PSE academic community, I will say, is the question, can these tools and techniques that we have made available to large multinationals, can they also be made available to our smaller brethren, the SMEs of the world? And this has traditionally not been possible because these models that we build come from data, come from very high-end analytics, come from various integrations, which have historically been accessible only to the larger companies. So when I talk about small, medium, micro-scale enterprises, we are talking about companies which really have very small plants, but as you will see in the next slide, they could be making a huge amount of usage of both energy and water. So for the purpose of laying an illustrative line on the sand, let me say that we are talking about small companies whose capital goods, meaning plant, machinery, etc., are of order of $1 million compared to Exxon, for whom a plant may be $1 billion or even higher. A medium enterprise may be one whose capex is order of whose total capital in the factory is order of $5 billion. These are the typical numbers that the Indian government uses, and I would suspect that a similar scale of investment is what a small or a medium enterprise in other parts of the world, including South Africa, would have access to. Now, what does that mean? Let's take a very concrete example to play with here. Let's take the cloth on our backs as we participate into this discussion. Textiles, right? Globally, about 100 million tons of textile is produced. The value of this is put at roughly 3 trillion, so that is 2% of the global economy. 2%. So it's not a small industry by any segment of any stretch of imagination. Now, this industry alone, just textile manufacturing, consumes 80 billion tons of fresh water each year. Now, do a simple math. 100 million tons of products produced, 80 billion tons of fresh water produced. Basically, we're saying to make 1 kg of cloth or fiber, this industry uses 800 kgs of water. So today, where we are in a situation where there are so many countries which are stressed for water, India being one, South Africa another, what would we not give to reduce the water intensity of a sector like this, like textile manufacturing? Okay. Now, textile manufacturing uses water in various activities as shown in the pie chart at the bottom of this slide here. Unfortunately, huge amount of this water, estimates put it at 40%, come out in a semi-treated way and is discharged to the environment, like you see in the picture on the bottom right. This causes further implications on the environment. The estimate is 1 liter of water or 1 kg of water which is discharged further pollutes another 5 liters or up to 8 liters of groundwater. So when you have a situation where you are taking out so much fresh water, 800 kgs per kg of product, 40% of it is discharged to the environment, which then goes on to then pollute other groundwater, you can see that the footprint of water by just this sector is very, very large. Now, this sector clearly should do whatever it can to reduce the freshwater intake and reduce the contamination that it puts out on the environment. Unfortunately, much of this sector is populated by small and medium enterprises, mom and pop factories. The question then that this community that we have around the room today, the question that we should be asking is, can we develop simple strategies to maximize water reuse, minimize the freshwater intake that a company like this, company operating in the textile sector, can it do simple things which is within its ambit of technology, within its ambit of sophistication to reduce water? Answer is, in fact, resounding yes in my view. So let me share with you an example that we have worked on with a company here in India. And I just want to emphasize right at the beginning that we're talking about this just as one example. This is not the only thing which is possible. This is one of a dozen things which could be done. I want to give you just a simple illustration. So we worked with a company which processes textile, one early stage. We're looking at one machine that is primarily the heart of their operations. This is called the soft flow dyeing unit. It takes raw material, which is in the form of yarn. It then puts it into this machine, which is several meters long. And then it carries out various operations. The purpose of these operations is to, one, wash and bleach the raw material textile in its raw form, then treat it various chemicals in order to make the make the cloth lustrous, in order to give it color through absorption of dye, and then for drying to remove the excess chemicals, and then eventually various operations to make the cloth, the textile, the yarn soft and make it rollable. The details I will kind of skim in the interest of time. What I want to convey to you is that depending on which grade or which color of product is being produced, in just this one unit, they may be doing up to 14 or 15 different steps as shown here. If it's a white product they're making, they may just do 4 or 5 steps, whereas they're making a dark color product, they may do 14 or 15. The plant, the unit, the cloth can spend up to 10 hours in the machine before it comes out. But over the course of these 10 hours, every few minutes or every 15-20 minutes, every 45 minutes, lot of fresh water is pumped in, sometimes with a lot of chemicals. And then after the chemical has soaked into the cloth, the water, which is a mixture of both fresh water and the chemicals, will be drained out and ideally sent to an effluent treatment plant. So this is a very simplistic view of the unit, but nevertheless, it would convey to you that a huge amount of water is in fact being used. So working with a company, we started asking, is there a way that we can somehow give them an ability to reduce the amount of fresh water that they will have to use? I will not dive too much into depth of the technology that we developed. I just want to say, convey to you the simplicity of what we're talking about here. We said, what if this plant has a few tanks, and all they're going to do is take the water which they pump out of this unit after the step is completed, and rather than send it directly to the water treatment plant, they will store it in an intermediate storage tank. And if a subsequent step can live with the chemicals which are in this effluent, this water will be used instead of fresh water for the purpose of the next step. Okay, so more chemicals may be added, but nevertheless, that processing step will not be affected. The quality will not be affected by the presence of the other chemicals which were gathered from the previous step, and therefore this water could be reused in some subsequent water consuming step. So we modeled that. We collected water, the quality of water which is produced as effluent in each of the processing steps. We calculated how much chemicals are present, do they interact with the subsequent processing steps, and so on. We developed a mathematical model and then used it for optimization. Again, given purpose of today's talk, I will not go into the details of the optimization. These details are reported in some papers that we have published, and I'm happy to share them with you if you're interested. What I want to convey to you is the amount of benefit which can be derived. Okay, so we used a genetic algorithm for solving this problem. The details, like I said, are not so important. I want to highlight that with this optimization, we found out that the plant could reduce the amount of fresh water they will have to use in their operations by 3/4, by 75%. So the fresh water, earlier they were using nearly 750,000 kgs for making a particular basket of products. We could reduce that by optimization to 180,000 kgs. So 3/4 of the water does not have to be used. If less fresh water is used, less effluent is also produced. That is 80% of the effluent can be done away with if we can reuse the water the way we have envisaged. This obviously comes at a bit of a cost. The cost, in fact, is in how long it takes to run the entire campaign. Earlier, if they were not reusing the water and they were depending only on fresh water, they could run the entire campaign in 32 hours. With water reuse, it would take them just 1 hour longer. Okay, with a small increase in the duration, instead of running it for 32 hours, they would now have to run it for nearly 33 hours. They could save a huge amount of fresh water. Now, this obviously, I'm sure all of you agree, is a significant improvement in the water footprint that this company, this plant could make. This required some small investment in these storage tanks that I talked about. In this design, we required them to have 13 different storage tanks. Obviously, that would take up space. It will take some investment. So we also then asked, is it possible that the company could reap not this entire benefit of 80% reduction in effluent water and 75% reduction in fresh water? Is there a halfway mark or a partway mark where they could just buy 1 or 2 tanks, because maybe that's all that is affordable to them, and still reap much of the benefit? And that's what these plots show, that in fact, with 2 tanks, as is shown by these plot here, they could reduce fairly significant amount of the water. So 42% of the fresh water compared to what they were doing earlier could be reduced by just having 2 tanks, and fresh water comes down, effluent water also comes down quite a bit, by roughly about 40%. So this, in our viewpoint, is a good trade-off. It has low operational complexity. That's a simple rule of thumb that we can provide to the operator, saying if this condition is met, send the water to the intermediate storage tank. If this condition is not met, then send it directly to the effluent treatment facility. Okay, very low capex requirement, order of $10,000, and a significant amount of wastewater reduction. So this is an example of how, with some analysis, one can develop fairly simple interventions that even a small, medium enterprise can use to reduce its water footprint. Let me give you, in the next 5 minutes or so, a very quick overview of another example, this time related to energy efficiency. All of you know that energy exchange is something that is bread and butter of running any chemical process. Now, this is done in heat exchangers. Heat exchangers unfortunately get fouled where coke or other impurities in the process material or in the utility fluids get deposited along the walls of the exchanger. So you see some pictures of fouling in the shell side of exchanger here and in the tube side of the exchanger here. What's the impact of fouling? It significantly degrades energy efficiency. Again, if you go to a large refinery, billion-dollar plants, they would have a fouling efficiency monitoring program. The question we have been asking is, how can we make these kind of technologies available to a small and medium enterprise? Again, I will not delve into the depth of the technology here. I just want to convey to you how this can be tackled. We have developed a simple graph, a graph paper of sorts, where a company can go take measurements. Does not have to be continuous measurements. They can go once a week to the heat exchangers, take some pressure drop and temperature measurements, plot it on this special graph paper that we have developed, and find out if the heat exchanger is operating in a clean zone or it is operating in this what we call alert region, where the efficiency has now degraded. So in this particular example, when a particular heat exchanger is being monitored, after 21 weeks of cleaning, they have found that the efficiency has dropped. It's still okay, but they should plan on cleaning this heat exchanger to remove the foulants in the next month or so. And what we found was that if they did not clean it for the next 5 weeks, in the week 26, the efficiency has dropped so much that they are now wasting a lot of energy to provide the same amount of heating that the process requires. Okay, so it does not require computers, it does not require optimization, it does not even require online instruments. All it requires is once a week, operator goes, takes some measurements, comes, plots it on this graph paper that we have developed, and it will give them a sense of how efficient is this particular heat exchanger. We also developed some technique recently for figuring out what is the Foulant which is decreasing the efficiency of the exchanger. And for example, in this particular case, by using some plots, we could show that the particular Foulant is not an organic, it's an inorganic, and therefore the factory should prepare for mechanical cleaning of the heat exchanger in order to make it clean. I don't have time to talk in detail about another example that I have here. So I will just again give you the overview. This is an example where we help a continuous processing, but a small scale facility, which in this case was handling milk to improve their energy efficiency. So this is a continuous plant. They have a series of equipment, evaporators, preheaters, and so on to process milk. What we found was that the original design was not using a lot of waste heat, which was actually available within this flow sheet. So we suggested some small improvements, small changes to their process flow sheet, which could offer significant enhancement, about 30% to their energy efficiency. So you see that with these small improvements in the flow of the utilities that they were using, their preheater could go from energy efficiency, exergy efficiency about 22% to exergy efficiency about 40%. And similarly, various other pieces of equipment could also undergo significant improvement in energy efficiency. So what I hope to convey to you over the last half hour or so is that planet Earth is in fact facing a very serious concern around both energy, around the issue of global warming and such, but also water, the availability of fresh water for all our users. Manufacturing overall has to play a significant role because manufacturing today uses significant amount of water and energy. Within that, the chemical industry. It's been my thesis that the large players have played a good role over the last 20 years or so in using optimization to reduce both energy and water intensity. They still have a long road to walk on, but the small and medium companies are the ones which have, in a sense, not participated at all in this journey. And what I hope to convey to you with the number of examples over the last half hour is that by manipulating, by changing the way we develop our technologies, process systems engineering can deliver solutions which do not require sophisticated instruments, which do not require high-end computers, which do not require model maintenance, and all those things which are beyond the realm of the SMEs. I hope this gives you a flavor of the kind of technologies which can be easily deployed to small companies. So with that, thank you very much for your attention. I'll be happy during the panel discussion to take any questions you may have. Back to you.
Thank you very much, Raj, for that very insightful presentation.